This is the technical presentation of the work that has been done to research the implementation of an inverse kinematic based approach to the reset mechanism in a reinforcement learning framework. I will start by introducing the technical aspects of the experiment, of the first experiment, and the technologies that were used. I will also talk about the problems and issues that were encountered in that part and how I dealt with those problems. And after that, I will do the same thing for the second and last experiment. The first experiment is a robotic grasping task where a Sawyer robotic arm um, with a Baxter gripper tries to grab an object on a table. The simulation training was done on the Coplia Sim simulator. It's a highly flexible robot simulator that allows objects to be controlled individually using via internal scripts or the Python API. It also has a package called PyWrap. It's basically a Python wrapper for Coplia Sim, specifically designed as a toolkit for robot learning research. It also provided me with a lot of with a range of robotic models that I could use for my prototyping. I have done some research on other simulators, but Coplia Sim was by far the most elegant one to work with, and they also provided they provided a lot of tutorials that made the learning curve easier. I was also a little bit biased because an external mentor of mine, Damien Bogunovic, sorry if I spelled pronounced the name wrong, published a tutorial of how you can use deep reinforcement learning to solve robotic challenges, and he also used Coplia Sim, so it was easier for me to make the connections of the tutorial that he published to my own work. To speed up the development and prototyping, I used PyTorch and OpenAI Gym. OpenAI Gym is a toolkit used for reinforcement learning research. I used an open source implementation of the SAC algorithm. This implementation allowed multiple agents to be trained in parallel using workers, basically multiple threads, CPU threads, which can reduce the training time. The implementation of the SEC algorithm was also redesigned to work with the OpenAI Gym. The hardware used for this experiment was on the Azure Porter platform, where I basically rented a CPU because GPUs were very expensive. But later on, I got my university provided me with a 2080 Ti paired with an i5 environment. So maybe let's start by giving an overview of the folder structure. I have it open here somewhere. It's this one. Yeah. Nope, it's not this one. Yep. Okay. Oop. So as you can see, there are 4 folders starting by the models. Here are all the trained models saved. And secondly, we have the robotics folder. Here, all the robotic models are being saved. And in the simulation folder, we have the basically the Coplia Sim environment. So it's basically the scene with all the objects in it. And lastly, we have our main folder, which is the source folder, where that contains the definition of the SAC algorithm. I'm not gonna go through the SAC algorithm because that's not the purpose of this project. But I will, tell you where everything is. So this is the SAC trainer, and it saves the model basically. And then we have the worker, which enable us to have multiple workers that can share the network parameters while being trained. So that will speed up the process basically. If you have a good GPU, if you don't, you're screwed. And then, we here you can find the hyperparameters are being defined. You give in the number of workers. It's you can also give in the number of CPUs. It's the same thing basically. And then then it starts basically it starts an environment. I will talk about the environment later, and then it gets the action space and the observation space. And yeah, that if the train argument is given, then it will share all the global parameters where with all the processes, and then it will start training basically. And if you call the test argument, it will go to the models folder, and it will run the model to see if load the model to see and give you the episode and its reward. And let's go to the environment. So this is the and basically where the environment is defined. We start by initializing all the objects. We launch the scene, and yeah, I'll explain the reward function later. Yeah, we detect all we call all the object in the scene, and yeah, we also set the observation and action space. Set the agent tip and target position for the inverse schematic chain, set proper initial robot gesture, step the physics simulation. A step in the physics simulation means just like, okay, now start basically. Then the get state method basically gets the state of the environment, which is the angle, the joint angle, and the velocities and the target position. The is holding method will check if so a proximity sensor is being used to see if there is a object between the two ends of the gripper. If that's the case, if that's the case and there's collision between the object and the two ends of the gripper, then yeah, then is holding will be true. The reinitializes the environment itself. Yeah, this is needed because sometimes the gripper gets broken during the exploration. I'll come back to the reset method afterwards. The step, yeah, the step basically just moves the robotic arm according to the actions given by the network, by the agent. And here we also have defined the reward function. So upon successful completion of the task, so grasping the cube, basically, the agent receives a positive, what line is this? 150. It receives a positive reward, so it's a plus 10. And if it's pushing the cube off the table, then it yields the same value but negative, so it's minus 10. This constitutes a sparse reward, and it's very difficult for the agent to learn. As a solution, a distance penalty was added to the gripper. So it's from the gripper to the cube, the distance in that, as well as the penalty for the collision between the gripper and the table to avoid damage to the gripper, which constitutes a dense reward. So you can also see all that. So this is the square distance, or the square distance between the gripper and the target object. And also, yeah, we close the gripper if it's close enough to the object, and the object is detected. So this will basically grab it. So it will grab the object if it detects it. If it detects it's between the two pads of the gripper. And we have our base reward here. And then in case when the object fall off the table, then we give it a minus reward. Yeah, the shutdown is just a method to shut down everything basically. Yeah, so that's it for the environment. What can I say more? Yeah, maybe I'll start the training up. Reset meetings. Okay. Why is it so difficult to find the rate? Okay. So yeah, we'll just run. So we'll run with the training first. Python source scikit-learn, and then you just call train, and then it will start the training basically. So it will start the CopySM environment, and it will visualize the training. I just hope everything goes as expected, because most of the time it only works when you're not showing stuff. Okay, so now you can see it's training. I'll let it run for a bit. Up. Yeah, and then that was a. So every 20 episodes, it will save the model, and then yeah, it will shut down the environment and start again. Now I'm only using one thread, so it's only training one worker. The training works, but the main problem, so the main issue here is the fact that it's not using the reset mechanism, and that's the whole purpose of the project basically. And why it's not using that? Well, I'll explain now. Basically, that's also the reason why I had to why I had to start a new experiment, because basically I tried. So I used the inverse kinematic module of CopySM for the inverse kinematic of the robot. So basically, when the robot, just showing. So when the robot was done with its trajectory or episode, then it had to reset the object. If it touched the object, then it had to reset it to the initial position. But I couldn't make the inverse kinematic works because of the inverse kinematic module of CopySM. So it always gave me an error that basically said that the distance between the gripper and the object, and the target object itself was too big, which resulted in zero robot, which resulted in a non-return from the inverse kinematic module, because there are no configurations, which is logic. So if the inverse kinematic module sees that the object is not in reach, then it will return none, and it will say that there are no robotic configurations possible to reach that position. But visually, the robotic arm was the object, the target object was always in reach. So, and I couldn't find any solution to that problem. So I tried alternatives. And I have so many things open here. Up. Okay. Just a second. So I tried to use the Python API communication. So previously I was using the PyRep method of communicating with the CopySM environment, but you can do it. You can do it with the Python API of CopySM itself, but that was too slow to to work with my with the reinforcement learning algorithm. So I couldn't use that. I also tried using insight scripts in CopyA Sim using Lua, which is a programming language. But you have to specify the inverse kinematic chain yourself, and the robot model was too complex, and I couldn't do that, or I didn't have enough time to be doing that, basically. So I had to find a different solution, and the solution was to start over again. Because of the failure of the first experiment, I had to start over again using a new simplified simulation task. The robotic arm had to learn how to pull a box to a goal position this time. So yeah, so it has to learn to this. The goal position is like 0.5 centimeters from the initial position, and if it moves it back but not good enough, then it will push it back to the goal position. It will push it back to the initial position, and then it will learn and try to pull it back. And when the box falls off the table, then it will reset the entire environment using a hard reset. What am I doing here? Reset the world. To simplify the problem, I used a ROS, which enabled me to use URDF, which is basically an XML format that allows robotic model definition in Gazebo. And Gazebo is this physics simulator or robotic simulator. And I used RRBot, which stands for Revolute Manipulator Robot, and it's basically a robotic arm with a simple 3-link and 2 joints. To further simplify the problem, the z-axis of the environment was removed, so the training could train faster. The kinematic model of the robot is relatively simple because of the dimensions of the robot. The lengths of the links are are 2 meters and 1 meter. Yeah, let's go over the project structure right now. Yeah, so as you can see, there are multiple packages. And ROS uses a packaging system. For you can find the meshes of the robotic models inside the RRBot description package. There you can also find all the XML definitions of the RRBot. And then we also have a we also have a RRBot control package. Secondly, we also have a RRBot control package, which allow us to publish the joint data to the robot, to the robotic arm using PID PID RAS control. And then as last, we also have our main folder or our main package, which is the RRBot RL. This has all the launch and environment setup. And it also has the model constraints, the joint constraints, basically defined with MATLAB. The robot class is defined as well in utilities. Here, it basically returns the configuration of the robot. So it returns a transformation matrix that has all the joints. And the inverse kinematics and the forward kinematics are also defined in here. That's all I think for this part. And yeah, in the utility folder, you can also find a noise class, which basically helps. There are different noise functions, but this one basically helps with the convergence of the model that is being trained. Um, the environment, if you go to scripts and then is there something else I should? No, yeah, the function, these two functions are just there for the weight updates. That's basically it. And then we have the environment. This is where we this is basically where the incoming and outgoing communication between Gazebo and the ROS controller is being are being done. So it will listen to the joint control date to the joint data, and it will also send the joint data back, so it goes to the simulation. And then we have also all the reinforcement learning methods that were defined. I'm not going to explain them again because I explained them in the first experiment. They're basically the same except the states. Now we have a 5-state we have 5 states and 2 actions basically, and they're calculated at each time step. What else can I say? Yeah, I'm gonna talk about the reward function, but I will do it later. Yeah, let's talk about the respawn. So there are two. So yeah, when you go to the reset method, if I find it, reset, you can see it's using a hard respawn model, which basically comes from the respawn module, and this has basically the definition of how the respawn, how the reset basically works. So there are 2 types of resets. You have a soft reset or soft respawn, or a hard respawn. The soft respawn is the default reset. So it's the instant simulation reset of the environment. This one doesn't use inverse kinematics, and we use this reset one when, for example, the box was out of the reach of the robotic arm, so then it cannot use inverse kinematics and path and trajectory planning to get the box, because there are 0 configuration to go to that position basically. um, Reset model. And then we have also a hard respawn, which is basically using the inverse kinematics and trajectory planning to push the box to its initial position when the environment resets. I'll show that later during the training, but I'll explain the reward function now. Where's the reward function? The reward. Uh, pa, pa, pa. No, it's environment. um, yeah. So yeah, there's like a whole so yeah, there's like a whole reward system. The reinforcement learning algorithm, it's the same algorithm, so it's the same soft actor critic algorithm that's being used. It will reward using different stages of the goal. Here the goal position is the position of the cube that is 0.5 meters distant from the initial cube position. The box thrown down the table will be rewarded negative, and once the goal is reached, a positive reward will be thrown. An optional reward based on the Euclidean distance between the initial and the final position of the cube can be also represented and implemented. The reward system is also defined here. And basically what's going on here is that when the robot is approaching the box, it will get a +2. When the robot is moving far from the box, it will get -50. When the robot is within the range of the of contact of the cube, it will get +100. And when the cube is moved to approach the goal, it will get +50, which is here. Yeah. And when the cube gets thrown away, it will get -500. Of when the cube is also moving away from the goal position, it will also get -500. Yeah, and there's also like a 20% threshold for when the cube is in within that threshold. So maybe let's start the training right now. Okay, something went wrong here. I'll just restart again. Uh, yeah, now I will just call the SAC algorithm. And basically it will start training. The SAC algorithm is the same one as before, so I don't need to explain it right here. Yeah, maybe I'll explain this later. Let's check. So now let's start the training. So we can see the state dimension is 5 and the action dimensions are 2. Yeah, so now it's training. And basically what it's trying to do is to get the box. It's trying to learn to pull the box to like here, which is the goal position. But sometimes it will like get it like let's move the box a bit so I can only move it like this. So this is not the goal position, but it's near. But now we want the box to be in the next episode. We want the box to be put back to the initial position, and we want to do that using inverse kinematics. Yeah, and as this in this case trajectory planning as well, and it will basically push the box back to its position. So it's taking this long because yeah, we basically move the box with our hands. There are also different reasons why this is taking so long. One of the reasons is because we set like a 1 second delay, and that's because the basically the reinforcement problem is too simple, and because of that I had to make a delay, make the simulation delay for like 1 second to be at the same, to be working at the same intensity. Yeah, intensity basically. Because if you don't do that, oh no, wait, okay. So now it sees it's in the wrong position, so it will move it to the initial position, which is here, and then it will start learning again. So yeah, I was saying that we give a 1 second delay for the training because not for the training, but for the simulation, because yeah, because otherwise the simulation will run so fast that it will throw the box when touching it, because yeah, the velocity is higher, and that's how physics works. And to avoid that, I made sure it was like there was a 1 second delay to avoid that problem. And yeah, also if you remove or the box is out of range, then it will instantly reset everything. Yeah, because because yeah, it's out of range. And that's how the training goes. Yeah, and when overseeing the training, basically, the robotic arm started approaching the cube around plus 40 episodes. And based on that observation, the training period should take more time despite the state and action space being small. The reason is due to the variation in physics of the model, resulting in a very confusing reward system. To overcome this, yeah, like I said before, I used a 1 second delay, um, which helps the robots stay stable. But this also costs us a lot of training time. The maximum time steps for an episode are 500 when training, and the models are validated every 10 seconds. That's what you get here, actually. So it's every 500. And yeah, and then it's saved every 200 episodes. And yeah, the plot, this one here that you can see, if you can see it, this will plot for a reward value for every 10 episodes once the models are validated. And yeah, this keeps the track of the convergence of the model, reducing the noise of the graph. So yeah, it's possible. I'm concluding now. So it's possible to use an inverse kinematic approach to the reset mechanism, but there are basically a lot of constraints when taking this approach. For example, like initially during the testing phase of the error bot for the forward and inverse kinematics, there has been a position error in the end effector frame due to the simulation based joint controller. um, PID control, like I tuned the PID control to an extent to overcome this issue, even though there are still some spots where there exist position offsets to the desired pose. And due to this, a reward function based on the end effector frame and box frame cannot be used for the training process. And I think that this also might be that the position error influences the weights updates of the critic network. Yeah, I would say the next or second constraint I came across is the inability of using path planning due to the physics and inertial parameters of the robot model. Since the robot model is too simple, the inertial parameters are based on assumptions and calculated based on the cubic properties of the robotic model. Yeah, the problem arises in position control, since the box is always thrown when the robot comes in contact with the box. Yeah, which is not very not very good. The trajectory planning, on the other hand, had which has which has a position, velocity, and acceleration control with operational space, also gave the problem of throwing the box. The training task, yeah, the training task has been changed to check the possibility of a successful reset, and the results are still the same in operational space. But I was successfully able to vary the joint step for the joint space-based trajectory, resulting in a better reset mechanism. But yeah, those are some constraints that I came that I encountered during this experiment. So yeah, this was it for the technical aspect of experiment number 2. Hopefully you like the project, and I see you during the presentation.